Once again, good morning to all of you guys. So in this video we are going to talk about this E1cB reaction. Okay, so before I start, I want to tell you that don't ask questions whenever I am teaching you. Whenever I will be asking you that is that clear or do you have any confusion, whenever asking you this kind of question, then do ask your question. Okay, then what will happen, you won't be getting irritated whenever you will be watching these recorded lectures. Okay, so I will be taking questions from your side whenever I will be asking you to ask questions. Fine, got it. So now what is about this E1cB reaction? Prakash, good morning. Roshni, good morning. So it's a very important reaction. So I have already taught you E1 reaction, sorry, E2 reaction. I have already taught you E1 reaction. Now I just want to teach you E1 small c capital V reaction, E1cB reaction. So what do you mean by this? So to understand this, let me recapitulate this E1 and E2 first. So I will be drawing only the skeleton, not the full structure. So suppose I have my living group over here and I have my hydrogen over here, right? This is this system generally participates in E2 reaction, E2 elimination reaction, that you know already. Similarly, I do have these kinds of systems. Here also I have living group and maybe I am having this kind of hydrogen over here. Fine. This system will also should have same kind of skeleton. I am talking about skeleton, okay? The living group and hydrogen. There is no difference in this. Why there is no difference? Because all these are elimination reactions. You can see this E for elimination reaction. Got it? So what is the difference then? So the basic difference, so you already know the difference between E1 and E2, already know this. But here I will be telling you something like difference between E1 and E2 and E1cB. How would you differentiate these two systems? So in case of E2 reaction, the living group is very good living group, definitely. So as soon as you incorporate the base will attack the hydrogen and will give you these multiple bond or these kinds of alkene, and you already know that this is your good living group, so it will definitely be released from the system, or it will instantly release the system, or it will instantly leave the system, because it's a good living group and this hydrogen is also more or less acidic. This hydrogen is also more or less acidic, okay? Acidic hydrogen. Fine, more or less acidic. Got it. So as this hydrogen is acidic, listen carefully. As this hydrogen is acidic, these base will come, and this base, every time remember, base has only one job. Wherever it sees acidic hydrogen, it will go and attack. This is the main job of a base. I am not talking about nucleophile. Nucleophile generally goes to the electrophilic center to attack. Nucleophile is used in nucleophilic substitution reaction. Okay, but what bases do? Bases generally try to find the acidic hydrogen, and whenever it is getting that acidic hydrogen, it will go and attack this hydrogen. Is that clear? Yes or no? So it will find this hydrogen as its acidic hydrogen and it will eat up this hydrogen. So once it is eating up this hydrogen, you will be getting this E2 eliminated product that you know already. I am not discussing it again. Coming to E1 reaction, same thing will happen, but the thing is opposite. In the first step, this living group will leave. Why it is leaving? Because it is also a very good living group, and it is also living from the system. And once it is leaving, what you will be getting? You will be getting this kind of thing, this kind of carbocation. Once the living group is leaving, because the living group is a very good living group, fine. So in the next step, the base will come and this base will again eat up this hydrogen and will give me the double bonded alkene product, like that. So you understood this one also. Fine, you understood this one also. Perfect. So this is my E2, this is my E1. Got it? You knew these two. But what about this E1cB? In case of E1cB, this living group is actually a very bad living group. That is the main issue with that E1cB. Not only that, this hydrogen is very acidic hydrogen. Here these hydrogens are what? These hydrogens are little bit acidic, because here you don't have any kind of electron withdrawing group, so these groups are donating electron. If any kind of alkyl groups are there, this group will donate electrons, and electron density will be as usual on this system. So as electron density is as usual, so this bond will not be that much weaker. Again, same is true for this. But in this case, this bond is very weaker. This bond is very weaker. Why is that? Because with this carbon atom, that means with this beta carbon atom, so with respect to the leaving group, this is my alpha carbon, this is my beta carbon, so this is my beta hydrogen. So with this beta carbon, I should have one electron withdrawing group that can show minus R or minus I effect. That means minus effect overall. So this kind of electron withdrawing group should present on the system with this beta carbon. So with this beta carbon, hydrogen is also attached. With this beta carbon, electron withdrawing group is also attached. So if it is attached to this beta carbon, definitely it will attract the electron from everywhere. So if it is attracting, definitely this bond will become very weaker, and because of this, if this bond is becoming weaker, so these hydrogen will easily leave the system. Whenever I will add any base, these hydrogen will easily leave the system in this way. So this is very acidic hydrogen, but the leaving group is not very good leaving group. Leaving group is bad leaving group. Okay, so you have got two features. First feature, bad leaving group. Second feature, very acidic hydrogen because of electron withdrawing group on beta carbon. Fine. So I hope you can see line this way. So that's all. That's the basic feature of this. So how do you understand that? Okay, this reagent, this substrate will undergo into the E1cB reaction. You just need to look at the leaving group, and you just need to the beta hydrogen, and at the same time electron withdrawing group will be attached to this beta hydrogen. Okay, so now tell me, is that clear? Have you got the basic idea? Of this E1cB reaction? Is that clear? I am talking about the basic idea. I will be giving you the complete mechanism and 10 different examples, 11 different examples I will be giving you, so nothing to worry about. Is that clear? Yes or no? Perfect. So now what about this bad leaving group? I told about bad leaving group. So I know I have written this bad LG, but actually I have to give you the example so that whenever you are seeing any substrate, you get to know, okay, this is the leaving group, but this is actually a bad leaving group. This is actually a very bad leaving group. So that bad leaving group is actually what? My fluorine. That could be fluorine, that could be OH group, or that could be like OR group. So fluorine, OH, OR, these groups are actually very bad leaving group. That means suppose with the carbon atom, you are having OH group. What you are getting? OH minus. It's not stable. Bad leaving group, not stable. Similarly, you are having like F. See, you already know 2p2p overlapping. It will not leave easily. Then if I am talking about OR, that means OCH3. So OCH3 minus, it's not very stable. So after leaving the system, the leaving group should be very stabilized. But it is not stable. It is not stable, and it will not leave because 2p2p overlapping is there already. Here also you can consider 2p2p overlapping. Carbons 2p orbital, oxygen 2p orbital. Overlapping is very perfect. Here also 2p2p overlapping. So overlapping is good, and after leaving it's not becoming stable. Because of that, these are very bad leaving group. Good leaving groups are what? Bromine, that can easily hold the negative charge. Iodine, sometimes chlorine is also good leaving group. Even like OH2 plus, if you are adding like another hydrogen with this, then this OH will become OH2 plus. Once you are releasing this OH2 plus, you are getting water molecule, that is very stable. So OH2 plus is very good leaving group, but OH, normal OH is not a very good leaving group. So bad living group means if you are getting this kind of living group in your system, you will be understanding, okay, these are my bad living group, so there is a possibility to go to undergo the reaction through E1cB reaction. Got it? Okay, so first I told you about this bad living group like things. Second important point is electron withdrawing group. So I told you I should have electron withdrawing group attached to the beta carbon. Attached to the beta carbon, I should have electron withdrawing group. So what are the different kinds of electron withdrawing group? Let me give you example. Electron withdrawing groups. So first electron withdrawing groups would be like C double bond keto group, electron withdrawing group that show minus R or minus I effect. Second, C double bond OH aldehyde group that also can show minus R minus I effect. Third, C double bond OR ester group that can also show minus R minus I minus R effect. Then like NO2 group that also can show minus I or minus I minus R effect. I think that would be enough. So all these groups are enough actually. Okay, all these groups are actually enough. These are my electron withdrawing group. All these group can show minus R minus I like effect. So how would you show that? That I will be discussing whenever I will be giving you example. So now guys, tell me, is that clear till now? Till now whatever I have taught you, is everything clear? Is everything clear? Because now I am going to give you the mechanism. How would you get the product? I am going to give you the mechanism. Is that clear? So I need comment from you. Is that clear or not? Why you are not commenting? Why guys you are not cooperating? If you don't comment, I think okay, you understood everything, so I will move forward. I won't ask you ever. So now what about the mechanism? Mechanism means how do you get the E1cB product? So as I told you, these features the system should have. These features the system should have to got into like E1cB mechanism. Okay, so in this system I told about this good living group. Good living group generally undergoes through these E1 E2 reactions, but living group is bad or electron withdrawing group is attached to the beta hydrogen, that makes the beta hydrogen very acidic. But these are like normal acidic system, normal acidic beta hydrogen, then it's fine, then you will be getting this. But if it is very acidic with the reason of this, if the living group is very bad living group, that means if these two conditions are being satisfied, then the system will be the system will undergo through the E1cB mechanism. Perfect. Now suppose let me take you one skeleton, but I am not giving you the right exact mechanism, exact example. Okay, I am just giving you normal idea. I am going to show you the mechanism. Okay, so look at this. This is my substrate. This is my substrate. Okay, so in this case what happens? This is my bad living group. So what happens in case of bad living group? Bad living group will say, so let me make some style. Bad living group will say, I don't want to live. I don't want to go. Bad living group will say, I don't want to go. So if it doesn't want to go, because here is a very strong interaction between this carbon and living group, then what will happen? This bond is very stronger bond, so this bond will not break easily. But you know, this hydrogen is very acidic. So this hydrogen will say, I am very acidic. This hydrogen will say, I am very acidic. So what will happen? This hydrogen is saying I am very acidic. So every time whenever you will be adding one base, what will happen? This base will come and easily obstruct the hydrogen, because this hydrogen is very acidic. and whenever it is obstructing, so I will be having like mechanism, but I am not showing you right now. Wait for some time. So it is very acidic. So whenever the base is very acidic, so it will just base, what base does, base generally obstructs hydrogen, acidic hydrogen. So it is very acidic, so it will easily obstruct this hydrogen. But this leaving group will say, okay, I don't want to leave, I don't want to leave, I don't want to leave. So if it doesn't want to leave, so can I do the E2 like mechanism in this way? No, I cannot do that. Or even I cannot do the E1 mechanism. Why? Because it is very bad leaving group, so it will not leave in the first step. So what can I do? As it is not leaving, it is saying I don't want to go, I will make the positive negative charge on the carbon atom. What product I will be getting? I will be getting electron withdrawing group attached to the carbon atom is having negative charge, again this, and finally Lg, which is bad. So this is my step 1. This is my step 1. So I have got a intermediate, I have got an intermediate after step 1, and that intermediate is actually a carb anion. That intermediate is actually a carbon anion, because I am getting negative charge on the carbon atom, and this negative charge is actually stabilized by EWG. This negative charge is actually stabilized by EWG, electron withdrawing group. Okay, this is stabilized by electron withdrawing group, and as this negative charge is being attracted by this electron withdrawing group, so overall carbon ion is actually stable. Overall carbon ion is stable. Got it? Got done. So this is my step 1. Then this is the intermediate. This is the intermediate that I am getting as carbon ion. Carbon ion is my reaction intermediate. Okay, so this is step 1. So in the step 2, what will happen? So let me copy this intermediate with its features and go to the next slide. So the next step, that means in the step 2, what will happen? Now you have got, this is your carbon ion. And how carbon ion is forming? This carbon ion is forming through the proton obstruction of this system, of this substrate. Okay, so now can you guys tell me, if any substrate is releasing proton, so what we call that this substrate is an dash? What we call about this substrate? What is the feature of this substrate? If any substrate is releasing H+, what will be the feature of the substrate? Can you write in the comment box? If any substrate is donating H+, definitely Rakesh, this substrate is called acid. And if it is acid, because it is releasing H+, so what product I will be getting? The product I will be getting, that is on negative charge. That means it will be called as a conjugate base. It will be called as a conjugate base. So this is my acid, this is my conjugate base. Now this is again my conjugate base, or I can write in shortcut CB. So now this conjugate base will participate into step 2. This conjugate base is also stable and is also a carbon ion, and it will participate into step 2. And whenever it is participating in step 2, what product I will be getting? EWG, C, leaving group is there. But look at this, look at this system. This is my system, but in this system, although this electron withdrawing group is present, this negative charge is on the carbon. So carbon is electropositive element, although it will stabilize the negative charge, but also at last, at the end of the day, carbon is having negative charge. That means the electropositive system is having negative charge, not favorable. So in the next step, it will do this kind of thing. But leaving group still says, please don't let me go. I don't want to leave. But forcefully, to neutralize the system and to make a very strong bond, that means double bond will generate. So double bond is more strong than single bond. So with that driving force, that the system will get a double bond, these of negative charge will come over here, and forcefully this leaving group will leave the system. This leaving group will leave the system. Okay, this leaving group will leave the system. That's all. So whenever it is leaving, so what I will be getting? I will be getting a double bond over here, and this leaving group will leave the system. So this leaving group is a bad leaving group, and it is not leaving. But whenever I am getting this negative charge, forcefully it will leave the system. Okay, got it? Perfect. Clear? I hope it's perfect. Okay. So because this proton is very acidic and this base generally obstruct the proton very fast, so the step 1 is actually very fast step. Step 1 is fast step. Now come to step 2. So in the step 2, what happens? In the step 2, as these kinds of mechanism is happening and this leaving group is saying I don't want to leave, so forcefully the system is leaving the nucleophile because it's a bad leaving group. So this reaction will be very slower reaction. That means the step 2 is slow step, and as it is slow step, so I can write the step is RDS or rate determining step. That means this will determine the rate of the reaction. So look at this, here step 2 is the slow step, but in case of E1 reaction, step 1 was, that means single step reaction, so step 1 was my RDS or slow step. In case of E1, step 1 was my first slow step. In case of SN2, step 1. In case of SN1, step 1 was my slow step. But in case of E1cB, step 2 is your slow step. So this is your alkene product. So now tell me, do you have any confusion in this? So I am just going to give you the examples, a lot of examples. But do you have any confusion till now? Yes or no? Yes. Okay. So now question arises that why this system is participating into this step 2, because it's stable. So it is what you are getting. You are getting a reaction intermediate, carbanion, carbocation, free radicals, carbene, then benzene, nitrene, all are called reaction intermediates. So whenever I am considering these reaction intermediates, so these are reaction intermediates, these are not the final products, and these will have this negative charge. So these negative charge is now neutralized. These negative charge, with these negative charge and with this electron withdrawing group, these negative charge gets neutralized. But at the end of the day, this is a carbanion. This is a carbanion. So carbanion is a reaction intermediate. It's not the final product. It's not that much stable like this substrate. It's not that much stable like this substrate. So because of this, as it is an intermediate, so it should form a product. So forcefully it will come over here, and what will be the driving force over here? Because if it comes here and leaves the leaving group, definitely it would get a double bond. So double bond is generally very stable. That will make the system very stable. And if the system gets very stable, that means the system will be more stabilized or less energetic. So to get that stability, this system, this carbanion, this intermediate is participating into this step 2, and that's why the step is slow, because it's not favorable. Leaving group doesn't want to leave. That's the logic. Do you have any other question? If you have, you can ask me. You can ask me if you have any other question. So why first step is very fast? The first step is very fast because you are adding a strong base or base, right? So if you are adding a strong base, what happens? This hydrogen is very acidic, and whenever this hydrogen is very acidic, that logic is what? Here you are having this electron withdrawing group to the beta carbon. This is alpha carbon, this is beta carbon. So because this electron withdrawing group is attached, so this group is 1 carbon, 2 atoms, first atom, second atom. This is attracting the electron density towards itself. So whenever it is attracting the electron density towards itself, this bond is getting weakened. So whenever this bond is getting weakened, so this bond is getting broken like that easily. That's why if it is getting broken easily, so definitely this hydrogen will leave the system as H plus easily. That's why the system is leaving H plus very easily, and it's a very good acid. And you are adding base, so base does what? Base just obstruct the hydrogen or H plus. That's why very acidic hydrogen will be abstracted through this base, and that's why as it is very acidic and also the carbon ion that is generating is stable, so this base will instantly come and accept this hydrogen. It will instantly come and accept this hydrogen. That's why it is first. That's why it is first, because it is very acidic hydrogen. Any other question? Any other question? If you have, you can ask me. Clear? Perfect. So I hope nobody has any other issue. Perfect. Good. So this is all about my reaction mechanism. Okay. So I will be giving you example. Perfect. Now if I draw the corresponding like energy profile diagram for this reaction. If I draw the corresponding energy profile diagram for the reaction, what I would get? Suppose this is my reactant. First let me come back over here. So how many steps are there in the reaction? Here I am having 2 steps. So as I already told you in the SN1, SN2, E1, E2 reaction, so each step, whenever a reaction, a reactant or a reaction is participating in a system, in a reaction, so in every step, this is my reactant, this is my product. So can I say that in the step 1, this is my reactant and this is my product? Definitely I can say that. Only I am talking about step 1, not step 2. In case of step 1, this is my reactant and this is my product. Right? Reactant and product. So if I am getting this reactant to product, so I will be getting this reactant to product through a transition state. So let me name this transition state as transition state 1. Okay. So this is one step. Similarly, this is in the second step. This is my second step reactant and this is my second step product. I can consider this. So in the step 2 also I will be getting another transition state because it is another step. So in each step you will be having one transition state. Fine. This is another state. Got it? So let me take this name transition state 2. This is my reactant. So from the reactant, from the first step, what I am getting? This carbon ion that is already stabilized, but it's although a reaction intermediate, so it is neutral system, but it is not neutralized. It has charges. That means it is not that much stable, but yeah, it is stable because of the electron withdrawing group that is attracting electron from the system, making the system stable. But it's what? It is stable, but not more than like reactant. Okay, but it is a reaction intermediate, and this is forming through this transition state. This is my reactant. So I am getting this transition state over here. Sorry, I am getting this intermediate, INT. I am getting this intermediate. How will I get? It will be formed through a transition state. This intermediate will be formed through a transition state, and that transition state is called transition state 1, isn't it? Definitely yes, because this is my step 1. Perfect. Now similarly, from the intermediate through step 2, from this intermediate I will be getting my product, and product is having double bond. That means very stabilized product. So again product will be coming over here. So I am not considering that overall reaction is endothermic or exothermic. I am not going into that either reactant or product above below like that. I am not now going into that. I am just showing you what will be my energy profile diagram. If it is endothermic, product will be here. If it is exothermic, product will be here. You know this already, but I am showing you the complete energy profile diagram. So whenever this intermediate is over, now tell me, now coming to transition state 2. Transition state 2 means what? This one. So transition state 2 is forming very slow. Why? Because the leaving group is bad, so it will not leave easily. So whenever it is trying to form this transition state, there is a driving force, and that driving force is double bond formation driving force, and because of that the reaction will happen. Okay, but this transition state is actually what? Is actually not that much stable. Why is that? It will be higher energetic. Why is that? Because this system, look at this system, it is very bad, it has very bad leaving group. So this bad leaving group will not leave the system very easily. So as it is not leaving the system, so definitely whatever you are getting, those will be like, this transition state will not be very stabilized, because transition state is the intermediate one. That means whenever I am getting this reactant to product, transition state is a state which has property of this and this. But whenever, as this is a very bad leaving group, so it will not leave easily. So because of that, transition state will not be that much stable. Transition state will be what? Transition will be very higher energetic. So in the step 2 again, from the intermediate, this transition state will go higher, and then it will give you the product. So this will be your transition state 2. So why transition state 1 is stable, like less energetic? So this axis represents energy, this axis represents progress of reaction or reaction coordinate. So why transition state 1 is stable, transition state 2 is not that much stable? Logic is simple. In case of transition state 1, so whatever I am getting, that is resonance stabilized. This negative charge is resonance stabilized. And in the same way, whatever you are getting, it is stabilized. But whatever you have, so this compound doesn't form. Like this transition state easily. So you can ask me one question, sir. In this question, you are considering this. In this question, you are considering this. And in this question, you are considering this. That means step 1, I am considering step 1 product. In the step 2, I am considering step 2 reactant. So why I am not considering that step 2 product is stable? So transition state should be very, very stable. Why I am considering that in this case I am considering that this is my step 2 reactant and it is not stable, it will not do easily, so transition state is unstable. And in the first case, this is stable, so transition state will be stable. Okay, that's why this transition state is very stabilized than transition state 2. So why I am considering in the step 1 this product, that means intermediate, and step 2 this reactant. That means step 1's product is intermediate, step 2's reactant is also intermediate, this carbon ion. So these and these are actually same. The logic behind this is remember the rule. Transition state 1 is very close to the intermediate. Transition state 2 is also very close to the intermediate. So can you remember that what was that? Could you remember this, like I forgot the name actually. Could you remember that, like what was that? Can you make me remember? That this intermediate has more property of this transition state, and this intermediate is having more property with this transition state. That's the postulate. I think I'm just forgetting it. I'm just okay, sorry. I can't remember that name. I taught you, right? I taught you in case of SN1, SN2, I taught you that one. Did you remember? Okay, let it go. So I am telling you the story behind this. This intermediate is very close to this transition state, or this transition state is very close to this intermediate, and also this transition state is very close to this intermediate. So because of that, the property of this transition state 1 is close to intermediate. So whenever I am taking the stability of this transition state, I am considering this intermediate. Similarly, I am considering this intermediate whenever I am talking about this transition state. Yes, Hammond postulate, yes. Hammond's rule, like that. Yes, definitely, Hammond's rule. Okay, so I am considering this transition state. So as product is far away from the transition state, so I will not consider that. So as this intermediate is very close to this one and also this one, so every time whenever I am talking about the stability of transition state, I will be talking about the stability of the intermediate. So in the step 1, this is my intermediate and this is very stable, so this is transition state is stable, and also this is very stable. But whenever I am getting the transition state from this, it is not stable because it will not easily leave. Transition state means in between state between the reactant and product, in between state of reactant and product. So this transition state 2 will not be stable because this is a very bad leaving group. Okay, got it? I hope it's clear now. So do you have any confusion till now? If you have, you can ask me. This is your step 2. Do you have any confusion till now? Now I will be giving you like examples, a lot of examples. Do you have any confusion? If you don't comment me, I will move forward. Okay, no comment means practice problems. Problem number 1. So here, what is the living group? Look at this OH. This OH group a living group, but it's a bad living group. So if it's a bad living group, so this is my alpha carbon, this is my beta carbon. So beta carbon does have its hydrogen that is very acidic. Why it is acidic? Because I do have this keto group over here. Because of this group shows minus R or minus I effect. Both of these effect is shown by this group, and because of that, this group will make this bond very weaker. And as this bond is getting weaken, so if I add a base like KOH, alcoholic KOH, for example, take alcoholic KOH, that will generate RO minus. I told you in the last examination. Alcoholic KOH, remember, whenever you are adding alcoholic KOH and your alcohol is ROH and you are adding KOH, so you will be getting RO minus. So these KOH, this will take this ACE and form RO minus. Remember, this is a very strong base, ASB, very strong base. Okay, got it? So if you are adding alcoholic KOH, what will happen? This base will instantly attack this hydrogen and obstruct it, and this will be my first step, and this is my step 1. Step 1, and after this, what you will be getting, as living group is bad, so negative charge will be generated over here on this beta carbon, like that. Try to remember the mechanism. Negative charge will be present over here and form the intermediate. So I will be having negative charge on this carbon. Here I am having living group, which is bad living group, like that. And these negative charge is generally neutralized. How it is neutralized? Because it can participate into resonance with this group, that is showing electron withdrawing effect. This is RC, RS, resonance stabilized carb anion, or conjugate base. I can write conjugate base, resonance stabilized conjugate base. Okay, so the next step, that is the, okay, this was your step 1. So the next step, what will happen? This system will participate into step 2. This will participate into step 2. So whenever it is participating into step 2, what product you will be getting? These negative charge will come over here, and this living group will leave the system, and this will be my slow step. Sorry. Now tell me, did you understand? Yes or no? I have done the same thing. There is no exception. Just try to accept or try to remember this one. Whatever information I have given you. What do you mean by alcoholic KOH? Okay. Try to remember this one. Do you have any confusion? Tell me, do you have any confusion? No. Yes or no? Tell me. I need comment, I need confirmation from you. Then I can move forward. This is question number 1. I have to give 11 examples. Okay, so you have to be fast. Why you are not commenting? Why? Okay, you don't have any confusion. Fine. So now I will be solving one queries regarding this. That why I am writing this reaction as my E1 small c capital B. Remember, small c capital B. why I am writing the name E1cB reaction. But before that, let me take one example. Conjugate base has the probability to form hydrogen bond with the second step. Then why second step? Okay, yes, this conjugate base, like after this resonance, it can form hydrogen bond. Definitely good observation. Now tell me, how much energy a hydrogen bond have? 5 to 10 kilocalorie per mole. Per mole, 5 to 10 kilocalorie per mole. So hydrogen, I told you already whenever I was teaching hydrogen bonding. So hydrogen bonds are not very strong bonds. So whenever this is participating into resonance, the negative charge gets stabilized. But here you are having one negative charge, right? So can you tell me, is this negative charge fully neutralized by this hydrogen bond formation? Yes or no? No. This negative charge is not getting neutralized through this hydrogen bond formation. It will get neutralized through real bond formation. So because of that, yes, it is stable. It is stable means this carbon ion is stable, but still it's a carbon ion. It's not a stable compound. It's an intermediate. Still it's an intermediate. Why you are forgetting? It's an intermediate which is stable. It's a stable intermediate. Okay, it's a stable intermediate. So in the stable intermediate, what happens? Some of you are having some issue with this resonance maybe. So what I have shown over here, from the first step I am getting this. One. So I am showing the stability of this one through the resonance. Okay, like this, with this green color. With this green color I have shown the resonance. With this I have shown the resonance. Okay, like this. Why I have shown the resonance? To make this clear that this is your stable carbon ion. That's all. That means with this electron withdrawing group, the system gets stabilized. But as you are getting this as your first step product, so this will participate in the second step. And in the second step, what it does? This negative charge generally does this kind of mechanism, and this leaving group leaves. So you will be getting double bond. Then this. That's what you are getting. Okay, clear? Clear, Prakash? Is that clear? Yes or no? Now my question is, why you are saying that this reaction is E1cB reaction? Why? This reaction is E1. E for what? E you already know, elimination. So you are not adding anything in the reaction, you are just subtracting, you are just eliminating parts. From here you are eliminating hydrogen, from here you are eliminating this leaving group. So you are just eliminating any part, that's why it's an elimination reaction. Perfect, got it. Second, 1 means what? It is called unimolecular reaction. So what do you mean by this unimolecular reaction? So unimolecular means unimolecular in RDS. Unimolecular means unimolecular in slow step or RDS step. So tell me, first step 1 in this E1cB reaction, step 1 is what? Step 1 is my very first step. So a very first step I shouldn't consider. But step 2 step 2 is slow step, or that step is also called RDS step. So in the step 2, how many molecules participating? How many molecules are participating? Only one molecule, this one. So as only one molecule is participating, so definitely the system will be unimolecular. The reaction will be unimolecular reaction, because in the slow step one molecule is participating. I don't need to see the first step, that how many molecules are, how many reactants are participating. No, in the slow step, how many reactants are participating? Only one. That's why it is unimolecular. I have to look at the slow step, because from the slow step I can determine the rate of the reaction. That's the logic. Okay. And what do you mean by this small c capital B? That means conjugate base, Cb. So as in the reaction you are having one conjugate base, it is your conjugate base. Try to accept, it is your conjugate base, it is your conjugate base that is participating into the slow step. That's why it is called E1 elimination unimolecular conjugate base reaction. That's all. That's the logic. Is that clear? Is that clear? So this is your homework. Okay, so this is I am giving you the hint. This is your bad leaving group, alpha carbon, beta carbon. Beta carbon does have two this kind of hydrogen, and with this beta carbon one electron withdrawing group attached. So I am using the base like same base. Okay, take it OET minus, take it OET minus base and do this, do the E1cB mechanism. So how do you understand that this reaction will participate into E1cB? Because the leaving group is bad and you have to abstract these hydrogen first. So this is your homework. Solve it and send it to benzene batch A/E. Just tell me guys, can you do it? Can you solve it? Yes or no? Can you solve it? Yes or no? This is question number 2. Can you solve it? Yes or no? Perfect. Now look at this similar type questions, but I will be solving this question over here. Okay, the reagent is my MsCl Et3n. Nitrogen is having this kind of lone pair. So this is actually a Claydon. Do you know the books is Claydon? You know the Claydon questions. Okay, you know the Claydon questions, and this is the Claydon's question. So this question is taken from the book of Claydon, so you know this one. Yes, I know it. It will be finished within 30 minutes. So Claydon's questions. Okay, so how do you solve this question? So if I ignore this, I will be having this. Nitrogen is having negative lone pair of electrons, and this will act as a strong base. This is very strong base. So now I hope you can do it. Okay, but I am solving you why? Because sometimes if you are getting MsCl, you may get confused. You may get confused that yes, I am. How do I deal with this? It's a very simple thing. So what happens? First, let me show you what is your MsCl. What is your MsCl? Methyl group, that means CH3 group attached to the sulfur atom, double bond O, Cl. This is your MsCl, that's all. So whenever you are adding MsCl, nothing will happen. Okay, nothing will happen. Just whenever you are adding MsCl to the system, just it will change the system slightly. This OH will become OMS. What do you mean by this OMH? Let me write now for this time. It will connect to this S, double bond O and Me. That's all. The Cl will leave the system, and with this bond is now there. This bond is now this bond. Okay, I hope you got it. Cl will leave, and this is your MsCl. So there is nothing to do. This is your again bad leaving group. This leaving group is your again bad leaving group. This is your bad Lg. Okay, so this is leaving group. So with respect to this is your alpha hydrogen. This is your beta hydrogen. This is also your beta hydrogen, but you cannot take it because already you have double bond over here. So you cannot take it. So with this beta position, you would have one hydrogen. Right? So now I hope you can do it. So let me do one thing. Let me complete this one in the next phase. Let me complete this reaction in the next phase. So now what I will be doing? Beta hydrogen NET3. I will abstract the beta hydrogen through step 1, and I will be getting this negative charge over here. OMS, I am writing OMS. Okay, I am not writing the full structure, negative charge over here, and with this negative charge this kind of group is attached. So I can do the resonance in this way. That means it is resonance stabilized, but I am not drawing the resonating structure. I hope you got it. This is how this conjugate base or the carbon ion is getting stabilized. So it is stable intermediate. So this is step 1. Now going to step 2. So the step 2, what will happen? These negative charge will come over here and will make this kind of mechanism, and this leaving group will leave. And what will be the product? CO2ET. Do you have any confusion in this question? If you have, you can ask me. So there is nothing to do with this MSCl. It will make the OH just OMS. It will make the OH as OMS. There is nothing like other things. Okay, there is nothing like no other things. All other reactions are same. If you don't change it, if MSCl is missing, then also you can do the reaction. Do you have any confusion? If you have, you can ask me. Otherwise, I am moving to the next question. Do you have? Yes or no? Okay, I need more slides. So give me 30 seconds. I should import more slides. Okay, I should import more slides. I'm sorry, just 1 second. Yes, I got it. Done, it's done. Okay, perfect. Now coming to next question. Question number 4. So I am giving you the product, but you have to do the mechanism. Here I will be using pyridine as my base. Okay, so pyridine nitrogen has lone pair and it will be my strong base. So this is your alpha carbon, this is your bad leaving group, this is your beta carbon. So beta carbon does have one hydrogen, and with this beta carbon you are having attaching this electron withdrawing group. Okay, so same thing will happen over here also. You are getting this bad leaving group. Okay, you are getting this bad leaving group. So again you are adding MSCl. That means in this system, this is your alpha carbon that is attached to this leaving group. This is your beta carbon. Okay, so beta carbon has your beta hydrogen that will be abstracted, and not only that beta hydrogen, with this beta carbon another electron withdrawing group is present, that is keto group. I told you already, keto group is my electron withdrawing group. So what will happen whenever you are adding MSCl? So this system will change into what? This system will change into CO2ET, OH. Just I will make, okay, I am sorry, I will make the OH at OMS, just like that, just like that. So once I am doing this, here I am having double bond O and I am having this H. Fine. So in this case, now I will be adding this base in this way, I will be getting negative charge over here on the beta carbon. Similar mechanism, similar, there is no difference. OMS, bad leaving group, negative charge over here, and this CO2 ET. So I have done step 1. I have done step 1, right? So this leaving group, again this carbon ion on conjugate basis resonance stabilized, that I can show through this mechanism. This is resonance stabilized. RS, perfect. In the next step, this is the first step product that I am getting. This is my first step product, okay, and in the next step this product will participate. So now coming to step 2, so let me copy it just from here. If you are not understanding anything, so ask whenever you are having problem. First of all, you have said everything is cleared a lot of time. Now you are saying explain step 2 again. I am giving you a lot of examples. I am explaining each of the examples, but you have to understand that is not possible every time. That's why I asked you, tell me whether it is clear or not. So after first step you are getting this, okay. In the next step what will happen? This is alpha beta again. This is my leaving group, bad. So now step 2, this leaving group will leave. And you will be getting this product. CO2ET. Okay, that's all. That is your product. Now tell me, do you have any confusion? Do you have any confusion? Yes or no? Do you have any confusion? Yes or no? Do you have any confusion? Yes or no? Yes or no? Okay, no confusion. Others are not commenting. Now, after one step, if you ask again that I have confusion, I won't explain you. Please. I expect comment from you so that I get to know that everything is clear to you. But if you don't comment and in the next step you would say again explain everything, I can't do that. Please. Because I have explained 3-4 questions like this. Same questions. There is no difference in this. So now coming to this question. This question is little bit different. Why it is different? First of all, you will be adding HCl H2O. Second of all, you will be adding this base. And the medium will be ether medium. That means this step will be your E1cB step. But the first step will give you different product. So what will be the final product? It's a reaction mechanism, okay. So whenever you are adding this HCl H2O, so it is not your E1cB reaction. So you have to get the product after step 1. After you add this reagent, okay. So once you add this reagent, you will be getting a product. That product will participate into E1cB reaction with this base. Get it? So let me show you how it is possible. So what you are doing, you are adding this HCl. That means acid. HCl is the HCl will generate H plus from the system, okay. So what will happen, these oxygen, as this is generating acid, this oxygen will take up this acid, okay, or it will try to take up this acid, but I am not showing you right now. I am showing you what will happen whenever you are adding this. Here you are having this lone pair and this center is electrophilic center. Why? Because I already told you this carbonyl center becomes electrophilic center because carbon is having delta plus, oxygen is having delta minus. Perfect. This. So once you are doing this, what product you will be getting? I'm sorry. So now I am just making the bond in this way. Okay, like this I am getting this. So in the next step, what happens? This oxygen will again try to get this double bond, and it will come and it will release this OET minus. So whenever you are releasing OET minus, it's not stable. At the same time, this oxygen is having also positive charge, so it will abstract its hydrogen as H plus. So from here you are getting H plus, you are getting OET minus. This will combine, and this OETOH will leave the system, and whatever you will be getting, that is your this. Okay, let me write this bond as your below bond. Okay, because like this. Okay, because in the reactant it was below. Now what will happen in the next step? Cl done. That is the reagent you are getting. That is the thing that you are getting up to step after this, after you add this one, after you add this one. Now you are ready to move forward to step 2, that means E1cB reaction. Fine, got it. So now let me take this one and participate into E1cB reaction. Now tell me, in the step whatever I have shown, do you have any confusion? Do you have any confusion? You can ask me. You can ask me, do you have any confusion? It's looking like complicated, but it's not complicated. Okay, it's very simple reaction. So first step is complicated, but not second step. Do you have any confusion? Do you have any confusion? Can you ask me? Can you tell me? So this is step 1, and step 2 this will happen. If you have any confusion, you can ask me. So I know what you are thinking. If you are thinking, okay, OET is better leaving group. OET is better leaving group. OET is better leaving group. Okay. OH, not OH. OET is better leaving group. Okay. OET is better leaving group. So why this will be? You will be getting this kind of product. But here you can think that Cl is more or less good leaving group. Cl is more or less good leaving group. But why it is behaving like E1cB reaction? It could react like E2 reaction. It will come and get, and this kind of. This is because this hydrogen is very acidic, because again you are getting the same thing, alpha beta, and with the beta carbon you are getting this electron withdrawing group attached to the system. And as the electron withdrawing group is attached to the system, definitely this will give you this product. Okay, this carbonyl intermediate. So once you are getting this intermediate, you can do the resonance to make this stable, and because it is stable, it will participate into step 2 to leave this Cl. Okay, so this is again Claydon's problem. I hope Claydon's book's problem. So you have to understand these things very clearly, and just need to practice, because you have understood the mechanism. You just need to practice. Okay, now coming to the another problem, question number 6. This will be your homework. This will be your homework. So don't think this question is very like bad. This is your leaving group. Okay, so now you can do it. This is your bad leaving group, or whatever you say. This is your leaving group. So this is alpha carbon, this is beta carbon, this is having one hydrogen atom. Now I hope you can do it. So what will happen? This hydrogen is acidic. Why? Because with this beta carbon you don't have any electron withdrawing group attached. But once you form this after step 1 in presence of any base means consider like NET3 base. After this base, whenever this base is abstracting this hydrogen, you will be getting this intermediate. So after this step 1, whatever product you are getting, this one, whatever product you are getting, this is not like attached to electron withdrawing group, but this is stabilized through this kind of resonance. So I hope you can do the resonance, complete resonance. So as it is stabilized, definitely it is intermediate, stable carbon ion or conjugate base. Perfect. And in the step 2, what will happen? These negative charges will come and leaving group will leave. The product you will be getting, this will be your product. Is that clear? Is that clear? Is that clear? Is that clear? Yes or no? Yes, Fujia. Yes, Fujia Rahman. Good morning. Yes, Fujia. Good morning. So is it clear? That is your product. That is your product. Now coming to, okay, I have to import one more question, 2 more slides. Okay. For the timing I am showing you over here. So now let me give you another question. Question number, I think 7. Bad leaving group, alpha carbon, beta carbon. This is your alpha, this is your beta carbon, right? Beta carbon, you are having this electron withdrawing group attached. With beta carbon, you are having your electron withdrawing groups attached, right? So because it is your electron withdrawing group, so now look at this. You can do the same thing with the base. Consider the base is your N×3 base. Do it. It is your homework and send it to the benzene batch A/C. Send it over here. Done. Question number 8. This is your leaving group. I am giving you the complete information so that you can do it. Alpha carbon, beta carbon. You are having hydrogen in the position, and also with the beta carbon you are having this electron withdrawing group attached. Do it with OET minus base. I hope you can do it. I hope you can do it. Just copy it and do it with the OET minus base. The same thing, E1cB reaction. E1cB reaction. Question number 9. Question number 9 will give you this kind of thing. Bad leaving group. OMe is your bad leaving group. Alpha carbon, beta carbon. Okay, you do have hydrogen over here. So with this beta carbon also electron withdrawing group attached. NO2, I told you NO2 could be your electron withdrawing group. So NO2 with electron withdrawing group is also attached with the beta carbon. So again you can do the same thing with this base. Consider N83 base. Do it and send it to the benzene batch A/E. This is your again homework. Question number 10. So there is nothing like above below group, you just need to do the normal mechanism. In this case of like E1cB reaction, there is nothing like stereochemistry, okay? You can do the normal mechanism. So this is your leaving group, bad Lg and alpha carbon, beta carbon. With this beta carbon you are having beta hydrogen, and with this beta carbon also you are having this electron withdrawing group. That means you can do this. So you can do it through this using this OMe minus MEOH base. Okay, so this will give you OMe minus base. So I hope you can do it and give me the product. This is again also your homework and submit it to the benzene batch A/E. Okay, done. Last question. Last question will be your about what? So now tell me, is this clear? Till now whatever I have shown, is everything clear? I will take maximum 5 minutes more. I will take maximum 5 minutes more. Maximum 5 minutes. Everything's clear? Yes or no? Till now, whatever I have taught you, is everything clear? Just make sure you understood everything. And I am giving you all the informations regarding that. So can I get, okay, perfect. Now last question that I will solve over here. So now tell me, out of these two, this is my fluorine and this is my chlorine. Both are my leaving group. Both are my leaving group, right? Fluorine is very bad leaving group. It is little bit good leaving group. So now tell me, these hydrogen or these hydrogen. This is hydrogen 1, this is hydrogen 2. Which one I should consider? Hydrogen 1 or hydrogen 2? Which one I should consider? Hydrogen 1 or hydrogen 2 I should consider? Which one I should consider? Can you tell me? Can you tell me which one I should consider? Let's see. Hydrogen A or hydrogen B to show E1cB reaction. Step 1, I have a base like OET minus. So which hydrogen I should consider? H1s. Okay. Prithivish, you know this already. So I am doing both of them. I am considering H1 and getting this carbon ion. I am considering H2 getting this carbon ion. Let's see what happens. Okay, I'm sorry. H2. Okay, I have done H2. That means I will be having H like this, and in this case I will be getting this. That's all. So now tell me, here this negative charge is also resonance stabilized with this benzene ring, and this negative charge is also resonance stabilized on the benzene ring. This is stabilized to the minus I effect of fluorine. This is also stabilized to minus I effect of fluorine. But another stabilization generally possible for this one. What is that stabilization? Chlorine has vacant 3d orbital. And because of that, this will participate in this kind of resonance. This is very important. This is very important. This is very important. So because of these kinds of resonance, this step will not happen. This step will give you a predominant product during E1cB. During E1cB, this step will give you the predominant product. Okay, so if you are getting this kind of predominant product, so this will participate into step 2. So whenever this will participate into step 2, how it will participate? This will come over here, and this fluorine will act as a leaving group, because this is my beta hydrogen now. So if I am using fluorine as my leaving group, but I already knew chlorine is my good leaving group, but I am not taking chlorine. With respect to chlorine, this is alpha, this is beta, so I should obstruct this hydrogen, but I haven't done it. Why? Because of the stability of the carbon ion that I am getting. So you have to consider the stability of carbon ion. Here this carbon ion is not stable like this carbon ion. This is more stable, this is less stable. So as it is more stable, you will be getting this kind of mechanism, and the final product will be this. Now tell me, is that clear why I am doing this? This will be your product. This will be your product. Tell me, did you understand why I am doing this? This is your step 2. This is your step 2. Slow step again. Step 1, first step. Clear or not? Yes or no? Yes or no? Or do you have any confusion? Yes or no? Yes or no? That's all. If you have understood, that's all about the E1cB reaction. So do all the assignments that I am giving you and send it all in the benzene batches. I have given you all the hints. How would you do that? Now I am going to draw a table. And this table is very important to understand whether a system will participate into SN1, E1, SN2, E2, what kind of mechanism. Okay. Overlap in AP is good, so Cl will leave. Okay. So now Rakesh's question is, overlap is good, so AP is bad leaving group. So I am not going to that whether AP can leave or not. It is bad leaving group, but that leaving group will leave later on. First in both the cases I will have this conjugate base. So now I have to decide which conjugate base is more stable. If it is more stable, definitely the corresponding hydrogen will be more acidic. So now tell me, this conjugate base is more stable than this, so this hydrogen will be more acidic than this. So hydrogen is more acidic, so base will attack where, which is more acidic, so it will attack over here than this. It will attack on H1 than H2. If this is attacking to the more acidic hydrogen, I will be getting this conjugate base, and this conjugate base is more stable. And conversely, I can say, as this conjugate base is more stable, in the corresponding system this hydrogen is more acidic. So as it is more acidic, so I will get this one, and at the end of the day, you know, it is your bad leaving group, so it leaves through E1cB reaction. That's what I am doing. I hope now it's clear. If you have still confusion, you can ask me questions. So poor nucleophile, weakly basic nucleophile, examples are like I minus, then RS minus, done. Strongly basic nucleophile, like RO minus, then strongly basic nucleophile. Okay, so I have to add something over here. So I could write the system in this way also. This is actually strongly basic nucleophile, unhindered, RO minus. This is the example. Okay, RO minus, this is the example. Here also I will be using strongly basic nucleophile, but it is hindered. That means steric hindrance will be there, likely to be DBU, or like tertiary BUO minus. So these are called strongly basic nucleophile, but these are like DBU, and those are hindered. This is size is bigger. These are bulkier in size. These are bulkier in size, and these are called strongly basic nucleophile, which are unhindered, RO minus. Similarly, weakly basic nucleophile, I minus, RO minus, right? I minus, RO minus. Similarly, poor nucleophile, H2O, ROH, like that. Fine. Here I will be putting like group, methyl halide, methyl group. Okay, so methyl group would have like CH3X. So here you cannot see anything, means here carbon is there and carbon is having 3 bonds with hydrogen, you know this already. Here I am adding primary 1 degree halide, like 1 degree unhindered halide, unhindered, like this. Not only halide, it's a living group. Okay, X means it's a very good, it's a normal living group. Okay, it's a living group, very good living group, or living group normally. It is 1 degree but hindered. So this will be X and this. So hindered means here you are having like more crowding, but it's 1 degree because it is attached to the one carbon. Is living group is attached to the carbon which is directly attached to one carbon. That means 1 degree it is. 2 degree. 3 degree, example will be like this, 3 degree, like this, and finally beta to anion stabilized. Or bad Lg. So at the last, this is called beta to anion stabilized. So anion in the beta position will be stabilized, or subsystem those are having bad living group. So if the system has bad living group, whatever my nucleophile or basic base is, whatever my nucleophile is strong, weak, poor, good, whatever my nucleophile or base is, if the system has bad bad living group, all the system will participate into E1cB reaction. All the system will participate into E1cB reaction. All the system will participate into E1cB, E1cB. This is the shortcut method. Okay, this is the shortcut method. Perfect. So if my nucleophile is 4 and methyl is this, so there is no reaction. Here also there is no reaction. Here also there is no reaction. Here you can have SN1, you can have SN1 or E1, but SN1 will give me better reaction than E1 because E1 is slow over here. If you have 3 degree system, you can have E1 or SN1 both. That means what I am trying to make you understand, if you have these or this, consider this. If you have these and these, that means if you have this substrate and this nucleophile or base, you can have these. So let me write fill all the box. That is your shortcut. How could you get the products? So that's all. That is the shortcut. So suppose you have very strongly basic hindered nucleophile like tertiary butoxide or DBU, and you are having 3 degree system. You will be having E2 reaction like that, and this E2 reaction will give you major product. I am talking about only major one. Okay, all the things I have given you, all will give you major product. Suppose 2 degree and strongly basic unhindered nucleophile. E2 reaction will give you major product. So I hope you got this. So you just need to get the substrate, get this. You will be given the corresponding nucleophile or basic system, and you will be getting the corresponding product. That's all. That's all about this video. And if you want to learn what is your DBU has a very hindered powerful base or nucleophile. DBU, that is looking like this. This is 7 membering, this is 6 membering. Okay, that is about DBU. And nitrogen does have this lone pair, and because of this lone pair, this system generally participates into. This system is very powerful nucleophile, powerful base, but it is hindered. So this RO- is unhindered but strongly basic. It is hindered but strongly basic. That's all. Hindered means very crowding. It is not crowding. So that's all about the video. I hope I have given you all the basic information from advanced to basic, and this is the shortcut table, and this table has been taken from Clarion book, so you can trust on this table. Okay, so that's all about this video. I hope this video will help you a lot, and that's all about this thing. Okay, so the E1cB reaction is completed. Then we will be moving forward to other chapter. Done. Bye bye. Meet you in the next video.